Hi, welcome to Data Structure and Algorithm series by Coding Ally. Coding Ally is a non-profit organization where we believe women and gender minorities should have a safe space and support system where they can foster their skills and career in tech. I'm your host Sue. Today we are solving this Leetcode 203 remove linked list elements. This is the agenda. First, I will read the problem statement. Then, I'll go through the thought process, followed by step-by-step implementation of that thought process in both JavaScript and Java. I will read the problem statement. Given the head of a linked list and an integer val, remove all the nodes of the linked list that has node.val equal to val and return the new head. Let's have a look at the example 1. We have got this linked list as shown here, 1, 2, 6, 3, 4, 5, 6. From the visual observation, we see that we need to remove these two linked list nodes, 6 and 6, because their value is equal to 6. So we've got the output is 1, 2, 3, 4, 5. In example 2, in here, in the input, you can see that there is no element in the head, and the value that we need to, the value is 1. So since there is no element, then we will simply return the empty linked list. This example gives us an edge case to consider, which is if there is no head, we just simply return head, which is the empty linked list. So next, let's have a look at this example 3. In here, in this linked list, all the nodes in the linked list is 7, which is equal to the value that we need to delete. So in this case, we need to remove all these nodes and we simply return the empty linked list. And this is the constraint. The number of nodes in the linked list is in the range between 0 and 10 to the power 4. Node.val, it's the node.val, the range is between 1 and 50 inclusive, and the value that we need to delete, the value is inclusive 0 and 50. There are a couple of approaches that we could use to solve this problem. Recursion and also iterative using the sentinel node or dummy node. In this video, I will only focus on the recursive approach. I will link the video where I go through the iterative approach. So let's think about recursive algorithm in general. All recursive algorithm must have the following. Base case, which means want to stop, and recursive call itself means call the function itself, and we need to walk towards the base case. So let's have a look at how recursion and linked lists are related. Linked list is a recursive data structure. Linked list is either null, which is represented by null, it is an empty linked list, or a node pointing to a linked list. So we've got an item here, it points to a linked list. So therefore, you can see that linked list is a recursive data structure, and therefore we can use this recursive approach to solve this problem. So next question, we can ask ourselves, can every recursive function be converted into iterative function? So the answer is yes. Any problem that can be solved recursively can also be solved using iterative approach, because recursive algorithm use the call stack. Iteration is just a special case of recursion till recursion. Let's start with the step-by-step approach. So step 1. Step 1 is the base case. Once the head is null, we have reached the end of the linked list and we simply return head. So example 2 and 3, it gave an illustration of this base case example. So example 2 is empty, so we just simply return head. Example 3, all the nodes are equal to the value that we need to remove, so we will simply return, after removing, we will return the output. Step 2. Check if the node value is same as the given value for deletion. If it is, then we need to return the recursive call with head.next. You might not be clear this concept now, but later I will walk through the recursive call stack visualization. So in here, let's have a look at this example. 6 is the head. The value that we need to remove is also 6. They are equal. In that case, we need to return and then move this node to the head.next. Step 3. This case is head.val. The value is not equal to the value that we need to delete. So in this case, 6 is not equal to 3. So in this case, we just move to the next node and we check. We continue to check and make a recursive call. Step 4, we will return the head, and by the end of it, the linked list that we will be returning is 3, 4 now. So let's go through the code. In this step, we need the base case. So this is the base case. Head, we check. If the head is null, we just simply return null. So we can ask ourselves, without this base case, what type of problem we might encounter? So let's have a look at this diagram. Whenever we execute any algorithm, it takes the memory, and this is the general memory layout. In here, you can see stack memory, heap memory, and initialize data, and test code. I will only focus on these two. Stack memory space here, it's for the local variable and recursive call execution. Heap memory space is for dynamic allocation of data structure. So if we don't have a base case, recursive call will be calling itself. There is no stopping. It will keep calling itself and it will go into infinite recursive call. The space needed to store this variable and information associated with each recursive call will keep growing and eventually take up the space from the heap memory once the stack memory space run out. So this is the Stack Overflow error. So this very line of code prevents the Stack Overflow error and stop when we reach to the base case. In step 2, this is step 2, we check if head.val is equal to val. In JavaScript, we can use this 3 equal operator. It's a strict equality checking. In here, we have to return. The key point is return, and then we have to call the function itself and then pass in the parameter, which is the head.next, because we need to move the head to the next node, and then we will check with the value. So else mean they are not equal. In that case, then we just simply move the head node and the head.next, and then we will call the function itself, and then we will pass in a parameter. Step 4, we will return the head. So it might be a bit confusing for you right now to visualize the recursive call stack. So let's do the visualization. This is the linked list example here, and the call stack, and RE stands for remove element. This is the function. At the beginning, we will pass in 6, which is the head node, and value that we want to delete is 6. So we check they are equal. Since they are equal, we need to return head.next. So this is the information that we put it into this implicit call stack. Here, after we move 3 and 6, they are not equal. Since they are not equal, we just simply move to the head.next. So in here, we will call this function itself 3, and then we will pass in 6. Next, we call the function itself again. We pass the parameter 4 and 6. They are not equal. Since they are not equal, we will move to the next node. So here, last step, second last, 6 and 6. We are passing in we will call the function itself. They are equal. 6 and 6, they are equal. So we need to return head.next. Next, remove elements. We are passing in now, 6. Now is the base case. So now we have reached the base case, so we have to return. So when we return, we will release the call stack, and this is the value that we've got, and then this is the result that we are returning, 3, 4 now. This is the new head. So let's discuss time and space complexity. We are visiting every node over the linked list once. to check whether the value is equal to the given value that we need to delete. So for that, the time complexity is O of n. In here, I have shown previously that we need to use the recursive call stack, which is this stack. So because we have used the implicit recursive call stack, the space complexity for this algorithm is O of n. We can simplify the code. Instead of writing remove elements and return and then if else in here, what we can do is we can move this line out, and we need to check every single element, every single node, and we need to check. So for that, we can bring that node line out head.next, and then we will call the function, and then we will pass in a parameter, and then we check for the value. If they are equal, then we will skip it, otherwise then we have to return the head. So this is the simplification of simplifying the previous code, and we can even simplify this further. Instead of using if else, we can use a ternary operator. So in here, the code concept exactly the same. The only thing change is that this line in return, I have used the ternary operator. If this meets the condition head.val is equal to val, we will return head.next. Otherwise, we will return head. So this is for the Java. Let's have a look at JavaScript. Since JavaScript, the concept is exactly the same, it's just the syntax is slightly different, the method is slightly different, but in here, even the code is exactly the same except this strict equality in Java in here, but in Java we've got this strict equality, but in Java we've got this. So exactly the same. First we check, and then we will move to the next node and then use the recursion. So we call the function itself, pass in a parameter, and in this deadline we are using the ternary operator and return the item appropriately. So stack time and space complexity is also exactly the same. Time O of n, space O of n, because of the implicit call stack use. So let's summarize what we have learned in this problem. We have learned that linked list is a recursive data structure. Using this concept, we use the algorithm and recursive algorithm. First is base case, and we call the function itself. We have also learned the stack and heap memory and why the stack overflow error occur, and how we can prevent that using the base case. And we have also used the step-by-step approach to solve this problem. So thank you for watching. Please make sure to subscribe and press the like button if you find this video useful. Join our weekly, fortnightly data structure, Wednesday data structure and algorithm night, where we organize peer-to-peer coding interview. You can find the event detail in our Facebook page. Thank you.